This story is about a step that once seemed almost inevitable, about how something close stops being reachable when you look carefully at the distance, about a planet that looks like a neighbor in the solar system, and about the silence in which that neighbor drifts farther than we would like to believe. This is not a conversation about rockets or dreams. It is an attempt to hear the boundary, the place where possible diverges from feasible. What is at stake here is not a single technology, nor even a single life. What is at stake is the belief that we can do more than we actually can. A ship sent beyond Earth's magnetic field ceases to be a vehicle and becomes a closed system, one where every fluctuation in pressure, every mass miscalculation, every computational error echoes back slowly to a place where a reply from Earth will take dozens of minutes. The body in weightlessness remakes itself quietly, without pain, and that silence is deceptive. Bones lose density, muscles lose strength, and radiation, which no human sense organ can detect, continues working through the hull every second of the journey. Added to this is something that fits into no sensor: months of isolation, exchanging messages instead of real conversations, the weight of knowing that home is far away and perhaps will not come back soon, or ever. And behind all of this stands yet another wager: whether civilization is capable of holding a single decision across decades without changing priorities or trading a distant goal for a nearby gain. And what do you think? What matters more when it comes to a step like this? Trust in the calculation or honesty about what we still do not know? Are we ready to admit that never in science is not a verdict, but a quiet absence of grounds to expect an event in the foreseeable future? Listen, this story is about the silence between the possible and the feasible, and about what lives in it. Mars occupies a special place in the human imagination that is difficult to explain by scientific characteristics alone. This planet orbits the same sun as Earth. Its days are nearly equal in length to ours, and its surface experiences changing seasons. Together, these features create a persistent sense of familiarity, almost kinship, a feeling that between us and this planet, there is nothing fundamentally insurmountable. It looks close enough to seem reachable, and at the same time distant enough to retain the allure of a goal still to be conquered. Precisely this combination transforms Mars from merely an object of study into a symbol of the next step in crewed spaceflight, a step that seems almost inevitable. The scientific approach, however, demands separating the feeling of reachability from the actual state of affairs. Orbital stations, landers, and rovers spent decades gathering data on the planet's surface, atmosphere, and geological history, and each such mission reinforced the illusion of gradually approaching the moment when a human being could repeat that journey in person. Between robotic exploration and a crewed flight there lies, nonetheless, a gap that does not reduce to simple scaling of existing technologies. It is a fundamental gap, one that touches the very nature of what human presence requires, as distinct from a machine. The first and most obvious difference lies in life support requirements. An automated probe can operate in vacuum, intense radiation, and extreme temperature swings without needing any environmental control. The human body is entirely unequipped for such conditions. Every parameter of the surroundings, from air composition to radiation level, must be continuously held within a narrow, allowable range. This turns a spacecraft not merely into a vehicle, but into a closed life support system, where any disruption of balance can produce serious and sometimes irreversible consequences for everyone on board. We look at Mars and see it is almost next door, the same system, the same sun. But almost and reachable are different words, and the gap between them lies not in rocket engines. The duration of the transit multiplies this problem many times over. Even at the most favorable alignment of the planets, the journey takes many months, and throughout that time the crew is far beyond Earth's protective magnetic field. Cosmic radiation, which near our planet's surface is largely absorbed by the atmosphere and magnetosphere, becomes a constant background factor in interplanetary space, unavoidable and unceasing. Modern science describes the nature of this radiation in detail, yet a reliable and sufficiently lightweight means of fully shielding people from it without substantially increasing the ship's mass does not yet exist. Mass, in turn, is tightly coupled to launch capability. Every additional kilogram of shielding material, water supply, or life support component requires additional energy to escape Earth's gravity. Rocket technology obeys the laws of mechanics and chemistry, and increasing payload capacity does not scale linearly. Complexity and cost grow disproportionately fast. A separate and critically important question is crew autonomy. In low Earth orbit, cosmonauts maintain continuous contact with the ground and, in the event of a serious emergency, can count on relatively quick evacuation or external intervention. A flight to Mars strips them of both of those options at once. The radio signal delay between the planets runs to dozens of minutes, and any real-time assistance from Earth is physically impossible. Return under emergency circumstances may be ruled out by orbital mechanics. This means the crew must be prepared to handle any contingency entirely on their own, in conditions of complete isolation. And that awareness itself is an additional psychological burden, one that presses constantly, not only in moments of real difficulty. The psychological dimension of isolation is frequently underestimated. Human beings are social creatures, and prolonged confinement in a restricted, enclosed space with a small fixed group of people creates a load that technical measures cannot resolve. Studies conducted at Antarctic stations and in dedicated isolation experiments reveal a consistent pattern. Even with careful psychological screening, tension, conflict, and declining cognitive function invariably emerge over time. In interplanetary flight, these factors compound on top of physiological stress and constant background danger, mutually amplifying one another. Loss of bone density, weakening of muscle tissue, changes in cardiovascular function, all of this is reliably documented in long-duration orbital missions and is not compensated even by regular exercise programs. A flight to Mars, followed by extended time on its surface in different gravity, creates further challenges whose cumulative effect has so far been studied only in the broadest outline. Already at this initial level, it is clear. The notion of Mars as the obvious next step in crewed spaceflight simplifies the true picture almost beyond recognition. Suppose the ship launches anyway, and Earth orbit falls behind. The first question arises immediately: what exactly awaits outside, in a space that offers nothing but distance? The distance between Earth and Mars is commonly treated as a variable that depends on the orbital positions of both planets. At closest approach, Mars seems almost like a neighbor, within the same system, nearby by cosmic standards. Yet even at such moments, this proximity is purely nominal. The space between the two planets is so vast that human experience holds no intuitive equivalent for comprehending it. It is precisely this distance that produces most of the constraints that cannot be eliminated by simply improving technology. It permeates every aspect of a possible flight, from orbital mechanics to provisions distribution to crew psychology. Interplanetary space is not empty in the usual sense, but it offers no support for travel. A ship that has left Earth orbit can no longer count on regular resupply, rapid external intervention, or flexible course correction without significant fuel cost. Everything needed for the crew's life, work, and safety must be loaded at the outset, and the greater the distance, the higher the demands on the accuracy of foresight and the absolute reliability of every system. The smallest error in calculation or design flaw, barely noticeable in orbit, may in interplanetary space produce consequences that no one will be positioned to correct. A flight to Mars is not linear motion in any ordinary sense. It follows the laws of celestial mechanics, where conserving energy often matters more than shortening the journey. The most realistic trajectories exploit the natural orbital motion of the planets. The ship gradually transitions from one orbit to another, following the sun's gravitational field rather than flying straight toward the target. The result is that fuel economy is achieved at the cost of time, and this equilibrium is a fundamental feature of all interplanetary travel. Attempting to cut transit time through hard acceleration would require a disproportionately enormous amount of fuel, making such an approach practically unachievable with current technology. The distance to Mars simply cannot be covered faster. Physics does not permit it, and that constraint permeates everything else. The duration of the transit carries not only technical but biological consequences. The human body is adapted to living under constant gravity and regular day-night cycles. In interplanetary space, those familiar rhythms are disrupted, and even with artificial reproduction of light cycles, the body's internal biological processes change. Time in flight ceases to be merely a calendar unit and becomes an independent factor of physiological stress, inseparable from the crew's condition. The communication delay with Earth is another direct consequence of distance. Radio signals travel at a finite speed, and on interplanetary scales that delay becomes fully tangible. A message reaches Earth after a substantial interval, and the reply returns with an equal pause. This rules out real-time consultations or ground control during critical situations. Every decision must be made on board without immediate external support, and that requirement fundamentally changes the character of crew training and the entire decision-making architecture. Errors made under these conditions may surface only when they can no longer be corrected. And it is precisely this feature that creates a particular, hard-to-model category of risk. Increasing distance also complicates navigation. In low Earth orbit, a spacecraft's position is determined with high accuracy using a developed ground-based tracking infrastructure. In interplanetary space, no such infrastructure exists, and the ship must orient itself using distant celestial objects and its own onboard instruments, whose precision must remain stable over many months. Minor errors, accumulating over time, can lead to serious deviations from the planned trajectory. At the same time as the ship moves farther from the sun, the intensity of solar radiation diminishes, which limits the potential of solar power and forces either an increase in panel area or a turn toward alternative energy sources, each of which has its own constraints and risks. The reliability of the power system under these conditions becomes critically important, since its failure at great distance leaves virtually no chance of recovery. While the ship travels for many months, something invisible to the eye and unstoppable by any maneuver acts on it without pause from outside. Space beyond Earth's magnetosphere is fundamentally different from the familiar environment. Most of the ionizing radiation that continuously streams in from the cosmos goes entirely unnoticed by a person on Earth's surface. The atmosphere and the planet's magnetic field ceaselessly and invisibly absorb and deflect it, requiring nothing from us. Beyond this natural shield, the conditions change fundamentally, and radiation ceases to be an exception or a rare event. It becomes the background state of the space between planets. Interplanetary space is threaded by particle streams of two fundamentally different origins. The first source is the sun itself. Its activity is accompanied by a continuous solar wind and periodic bursts of charged particles, the most dangerous of which are solar proton events, powerful, short-duration fluxes capable of substantially elevating radiation exposure within hours. Predicting such events far in advance with high accuracy is not possible, and current monitoring systems provide only limited warning time. The second source is galactic cosmic radiation, composed of particles of exceptionally high energy arriving from beyond the solar system. This flux is relatively constant. It does not depend on the ship's position relative to the sun and constitutes a long-term accumulative burden accompanying the crew throughout the entire flight. Ionizing radiation acts on the body not as an instantaneous threat, but as a cumulative process. Charged particles pass through cells, damaging molecules, including DNA, and while some of these damages are repaired by natural mechanisms, as the total dose grows, the probability of errors in that process steadily increases. Consequences may manifest long after the exposure, which substantially complicates risk assessment during mission planning. Tissues with a high rate of cell division show particular vulnerability, as does the nervous system, which responds to prolonged irradiation with changes that have so far been studied only partially. Radiation shielding in space inevitably runs into an engineering paradox. Effective shielding requires materials of significant thickness or mass, and the more reliable the protection, the heavier the ship becomes. Every additional kilogram of shielding layer demands additional fuel for launch and trajectory correction, which brings us back to the fundamental constraints of interplanetary logistics. Improving one parameter inevitably aggravates another. Concepts for active shielding, creating artificial magnetic or electric fields around the ship, capable of deflecting charged particles the way Earth's magnetic field does, look attractive on paper, yet in practice they encounter serious difficulties. Powerful, stable energy sources are needed. Large volume fields must be generated, and their interaction with onboard systems requires precise control. For now, such solutions remain at the level of experimental models, unvalidated by prolonged application. Even with shielding, the question is not fully resolved. High-energy particles interacting with shielding materials generate secondary radiation, and the ship's interior becomes a complex mixture of diverse streams whose aggregate effect is difficult to evaluate precisely by calculation. Uncertainty persists even in the best designed systems. Mars itself offers no relief. The planet's atmosphere is hundreds of times thinner than Earth's and absorbs almost no cosmic radiation, while a global magnetic field capable of deflecting charged particles is virtually absent. Radiation levels on Mars's surface significantly exceed those on Earth, and extended stays there will require specially shielded shelters, possibly using local soil as a screen or bringing protective materials from Earth, which again returns to the problem of mass and logistics. The body accumulates dose continuously and imperceptibly. Cells are damaged, consequences compound. Radiation is only one of the invisible adversaries. The next is hidden inside time itself. In every additional month spent away from Earth, the duration of the flight to Mars is not merely a question of comfort or patience. It extends far beyond the familiar experience of crewed space missions and is determined by the fundamental laws of celestial mechanics. Motion within the solar system obeys gravitational interactions, and any attempt to substantially cut transit time demands disproportionately large energy expenditure. Optimal trajectories between planets are designed to make maximum use of the natural orbital motion of celestial bodies. The ship gradually transitions from one orbit to another, following the sun's gravitational field. This process resembles a slow insertion into the system, where speed and direction change smoothly and carefully. The result is that fuel economy is achieved at the cost of time, and this equilibrium is central to all interplanetary travel, admitting no alternative approach without a fundamental change in the very concept of movement through space. Prolonged confinement in an enclosed volume creates stresses that cannot be reduced to technical difficulties. The human body evolved in an environment of constant gravity, variable illumination, and a wide spectrum of sensory inputs, all of which served as an unchanging backdrop across vast evolutionary timescales. In interplanetary flight, these conditions change sharply and fundamentally. Microgravity acts simultaneously on bone tissue, muscles, and the cardiovascular system, triggering adaptive processes that cannot be fully halted by any amount of exercise. The experience of long-duration orbital missions shows the body gradually adapts to weightlessness, But that adaptation carries a real physiological price. Reduction in bone density, changes in muscle tone, redistribution of fluids in the body, all of this happens slowly and often imperceptibly to the person themselves, becoming apparent only upon return to gravitational conditions. In the case of a flight to Mars, the situation is further complicated by the fact that after the prolonged transit, the crew arrives not on Earth, but in an environment with a different, though weaker, gravity. This means a new adaptive stress with no transitional period. A body already reconfigured for weightlessness must reconfigure again, under conditions that match neither familiar Earth gravity nor zero weight. What that transition will look like remains largely unknown. The long flight affects both the nervous system and the mental state of every crew member. Months in an enclosed volume with constant instrument monitoring, a rigid schedule, and a limited circle of people create conditions of chronic stress that no technical countermeasure can resolve. Even with the most careful psychological screening and preparation, it is impossible to fully prevent the accumulation of fatigue, declining concentration, and shifts in emotional baseline. The absence of any possibility of quick return or external help is itself a pressure that is present in the background at all times, even during calm periods. The total mission duration, the outbound transit, time on the planetary surface, and the return journey adds up to years. Most of that time is spent in an environment the human body is not adapted for, and the accumulation of effects on those timescales has been studied by science only approximately. The body in weightlessness does not stand still. It remakes itself quietly, without pain. And then on Mars, it will have to remake itself again. Science can assess average risk for a group, but for an individual person, only a probability, and that uncertainty remains an inseparable part of any realistic plan. Beyond the average dose load that can be roughly calculated for a mission overall, there is a dimension that calculations capture far less reliably: the individual vulnerability of each crew member. Galactic cosmic radiation cannot be avoided by changing the flight trajectory or choosing a different launch time. It is isotropic, arrives uniformly from all directions, and constitutes an irreducible background flux throughout the entire interplanetary journey. No maneuver and no schedule can help avoid this component of the radiation environment. Heavy charged particles in galactic radiation present particular biological complexity. Passing through living tissue, they leave dense ionization tracks, damage that the body's natural cellular repair mechanisms compensate far less effectively than damage from lighter forms of radiation. The accumulation of such disruptions in DNA increases the probability of delayed consequences that may not manifest either during the flight or immediately after return. Data on the effect of precisely this type of radiation on humans remain incomplete. Conducting experiments in full scope is restricted by ethical considerations, and results from studies on cell cultures in animals do not allow definitive predictions for an individual. To this is added substantial individual variability. Different people's responses to the same radiation dose differ depending on age, health status, and genetic makeup. What will produce no noticeable consequences for one crew member may have serious long-term effects for another. During an interplanetary mission, there is no possibility of individually adapting flight conditions for each person, and this creates both a medical and an ethical problem. Consequences may appear only after the mission is complete, at which point neither the crew themselves nor the society that authorized the mission will be able to prevent them. The body changes from the outside, slowly, without symptoms, but no less profound changes occur from within, at the level of every system that sustains life. The human body took shape under the conditions of Earth's surface, where gravity, atmospheric composition, and environmental rhythms remained relatively stable across vast evolutionary intervals. All the major physiological systems, from musculoskeletal to cardiovascular, are adapted precisely to these conditions, and moving beyond them does not cause an immediate loss of function, but triggers slow changes that become noticeable only with time. Under the conditions of interplanetary flight, these changes layer on top of one another, forming a cumulative load that is difficult to forecast. Body weight creates constant mechanical loading on bones and muscles, maintaining their structure. Under conditions of prolonged weightlessness, the demand for that loading disappears, and the body begins to reconfigure. Bone tissue gradually loses density, muscle fibers lose volume and strength. These processes are consistently recorded in every long-duration orbital mission, and even regular exercise only slows but does not stop them entirely. The circulatory system also changes. In weightlessness, fluids in the body redistribute as the familiar action of gravity disappears. Blood and interstitial fluid shift toward the upper part of the body, pressure in the vessels changes, and the heart muscle adapts to a reduced workload. Returning to gravitational conditions after a long flight is accompanied by a complex and often difficult period of readaptation. A separate problem is the functioning of the vestibular system. The sense of body position in space on Earth is formed by a combination of signals from the balance organs, vision, and muscle receptors. In weightlessness, these signals begin to contradict one another, which can lead to disorientation, nausea, and impaired precision of movement. The brain partially adapts to this state over time, but full restoration of normal spatial perception occurs only after return to a gravitational field. At intermediate stages, the person is forced to operate under altered spatial awareness. The immune system also responds to the combination of isolation conditions, an altered day-night schedule, and chronic stress. Immune responses weaken, and some latent viruses may reactivate. In an interplanetary mission, this creates an additional risk, since options for medical intervention are strictly limited and evacuation is entirely off the table. The body adapts, reconfigures itself to survive, but on Mars it will have to reconfigure again, and the data for a reliable forecast are still insufficient. Meanwhile, from the outside, something the body is entirely unable to sense acts on it without pause. One of the fundamental characteristics of ionizing radiation is its complete invisibility to human sense organs. Radiation causes no pain, no sensation of warmth or tingling at the moment of exposure. This means that a person is entirely without the ability to directly feel what is happening to their body. Monitoring is carried out exclusively by instruments, and decisions are made on the basis of calculations and predictive models. In a long interplanetary flight, this means constant trust in those models, trust that cannot be verified by direct experience, and that itself demands a certain psychological resilience. The primary sources of radiation in interplanetary space are solar activity and galactic cosmic radiation. Solar activity is accompanied by a continuous solar wind and periodic bursts of charged particles whose intensity varies but never reaches zero. Galactic radiation originates in processes far beyond the solar system and consists of particles of exceptionally high energy moving at nearly the speed of light. They penetrate significant layers of material, interact with body tissues at the cellular level, and cause damage, some of which is repaired by internal mechanisms, but as dose increases, the probability of errors in that process steadily grows. Consequences accumulate slowly and may appear years or even decades after exposure. On the surface of Mars, the situation does not improve fundamentally. The planet's atmosphere is many times thinner than Earth's and absorbs almost no cosmic radiation, and Mars has virtually no global magnetic field capable of deflecting charged particles. Radiation levels on its surface significantly exceed those on Earth, and extended stays there will require specially shielded shelters, using local soil as a screen, or bringing protective materials from Earth. Each of these options is itself a complex, independent engineering and logistics challenge. The most troubling thing about radiation is not that it is dangerous, but that it cannot be sensed. Only instruments know the truth about what is happening to the body right now. But a human being is not only a body. Beyond physiology begins a dimension that is even harder to monitor with instruments. Behind the technical and physiological constraints, there exists one more level that no sensor can measure: the mental state of a person under conditions of prolonged isolation, confined space, and complete separation from everything familiar. In interplanetary flight, the psyche becomes just as much a functional component of the overall system as the ship's hull or the life support system, yet its behavior obeys far less predictable patterns, and science does not yet have reliable tools for forecasting it. The experience of terrestrial analogs, polar stations, submarines, long-duration isolation experiments, partially illuminates the possible consequences. These environments show, even with careful selection and serious preparation, people inevitably face gradual shifts in their emotional state. These accumulate slowly, almost imperceptibly to the participants themselves, and it is precisely that slowness that makes the problem most difficult to control. However, between a terrestrial isolation experiment and an interplanetary flight, there is a fundamental difference. Experiment participants always know that the exit is nearby, even if nominally prohibited. A crew en route to Mars is entirely deprived of that knowledge, and it is precisely that awareness that changes the very nature of isolation, not quantitatively, but qualitatively. Communication with Earth, when delays reach dozens of minutes, becomes not dialogue, but an exchange of recorded messages with a pause between turns. The living sense of another person's presence disappears, and communication becomes asynchronous, more like correspondence than conversation. The confined volume of the ship affects the perception of time. Without any change of setting, the boundaries of days blur. The rhythm of life is maintained artificially according to a schedule bearing no connection to natural cycles. Monotony under such conditions becomes an independent source of stress, gradually eroding concentration and motivation, even in people with high stress tolerance. The social dynamics of a small crew in an enclosed space also follow their own hard-to-manage logic. Any tensions between people cannot be released by a change of setting or temporary distance. There is no change of setting, no possibility of real solitude. Even minor disagreements acquire disproportionate weight over time, and maintaining stable relationships requires constant attention and internal resources that are themselves not boundless. There is also the factor of background danger. The knowledge that any serious malfunction may have irreversible consequences creates a sustained level of anxiety that is present at all times, regardless of whether anything is actually happening in the moment. Psychological support from Earth has limited capacity. Specialists can analyze the crew's condition and offer recommendations, but they exist in a fundamentally different environment, and that gap cannot be bridged by any technical means. Psychological limits are a real boundary, past which the flight ceases to be manageable. And even if the crew manages their inner state, the question remains: who on Earth is capable of sustaining such a mission across decades without shifting priorities? An interplanetary flight is never exclusively a technical event. Behind every launch stands a complex system of social decisions, economic commitments, and long-term political will. Even in theoretical form, a flight to Mars requires not only a rocket and a ready crew, but stable civilizational support sustained over many years. Support that does not break when governments change, does not dry up when new budgetary priorities emerge, and does not dissolve when the generation of specialists who began the program moves on. An interplanetary mission is by its nature longer than any familiar political or budgetary cycle. It extends beyond a single government, a single financial horizon, and even a single generation of engineers and scientists. Decisions made at the initial stage must retain their relevance and funding in a constantly shifting context: political, technological, and social. The history of major space programs shows that such continuity is the rare exception rather than the rule. The financial aspect is not limited to the cost of the launch itself. Behind it lie decades of development, testing, infrastructure maintenance, and personnel training. These expenditures yield no quick, tangible result that could be concretely shown to society, and the result is an inevitable tension between long-term scientific goals and short-term social expectations. Public support for space projects is largely determined by their tangible, practical benefit. Satellite navigation and communication systems, Earth remote sensing, automated interplanetary missions all have obvious, incomprehensible applied results. A crewed flight to Mars is far harder to connect with the daily lives of most people, and this inevitably raises the question of whether such an allocation of resources makes sense at the scale of an entire civilization. The ethical dimension adds yet another layer of complexity. A mission with a high risk level raises questions about permissible limits. And even with the crew's voluntary participation, society bears responsibility for the conditions in which these people find themselves. Discussions of such decisions inevitably move beyond science and touch on fundamental beliefs about the value of human life and the acceptable bounds of risk. The international character of space exploration expands capabilities through pooled resources, but at the same time creates dependence on political stability and mutual trust. Shifts in priorities or conflicts on Earth directly affect projects designed for decades. The problem of knowledge continuity is no less acute. Long-term programs require the transfer of accumulated experience between generations of specialists, and that process rarely occurs without significant losses. Shifts in technologies, standards, and approaches can devalue work already completed and require it to be revisited, pushing the moment of final decision further away once again. The history of space programs offers a cautious but eloquent answer to the question of what happens in the absence of sustained continuity. And finally, the most honest question: is science capable of providing reliable forecasts at such time horizons at all? A conversation about a crewed flight to Mars inevitably leads to the boundaries of predictability as such. Science works well with processes amenable to experimental verification or observation within relatively short timeframes. Interplanetary flights with human crews require forecasts decades ahead and sometimes over even longer intervals. And it is precisely there that the line runs between what can be calculated with sufficient reliability and what inevitably remains conjecture. Any assessment of the prospects for such a flight rests on the assumption that conditions will remain stable, that technological development continues in the needed direction, that resources remain available, that social and political systems retain the capacity to support long-term projects. Historical experience gives no grounds for treating any of these assumptions as guaranteed. Changes that seem insignificant in the short term accumulate over time and can substantially alter civilization's capabilities. Technical forecasts have analogous limitations. Engineering calculations describe individual systems well, but complex assemblies in which human beings, technology, and environment interact behave less predictably. Minor deviations in interplanetary flight may produce consequences that cannot be fully modeled in advance, not because science is insufficiently developed, but because the system's complexity fundamentally exceeds the capacity of any model. There is also the problem of gradual goal drift. Research programs shift emphasis in response to new discoveries, and each automated mission to Mars refines the picture of the planet while opening new questions. In this process, a natural question arises. Does physical human presence remain necessary to achieve scientific results? Or do robotic systems and remote investigation methods prove more effective and significantly safer? New methods of data analysis and the development of autonomous systems are gradually changing the very concept of what it means to explore in space. Abandoning a crewed flight to Mars in this context does not look like defeat. It looks like adaptation to real constraints. Never, in a scientific context, is not an absolute prohibition and does not mean physical impossibility. It is the silence with which science responds to questions for which it does not yet have sufficiently reliable data. The absence of grounds to expect an event in the foreseeable future, not a claim that the event is fundamentally unachievable. A human flight to Mars does not contradict known laws of nature, but its realization requires a simultaneous fulfillment of a great many conditions: technical, biological, psychological, economic, and political. The probability of such a convergence decreases as one must make forecasts over progressively longer horizons, and every new link in the chain of assumptions adds its own uncertainty. The idea of a flight to Mars took shape in an era when technological progress was perceived as continuous forward ascent, knowing no pauses. Modern science views development more soberly, acknowledging its cyclicality, unexpected halts, and possible changes of direction. In this perspective, interplanetary ambitions become one of the possible vectors, but not a mandatory or inevitable stage. It is important to distinguish imagined reachability from practical feasibility. What can be convincingly described as a project or scenario does not always find its way into reality. It is precisely the gap between these two levels that forms the space in which the assertion lives, that a human flight to Mars in the foreseeable future lacks a reliable foundation. It does not deny science. It is based on a careful and honest relationship with science's limits. In this gap between the possible and the feasible, in the silence with which science meets questions that have no ready answers, Mars continues to exist as a goal, slipping away precisely as far as it seems close. Please write in the comments how this story landed for you. It genuinely matters to me to know whether it reached you. What do you think? Should humanity invest decades and resources into a crude flight to Mars? Or is it more honest to acknowledge that this goal is currently beyond our capabilities? And one more thing, do you prefer watching a horizontal video or a vertical one for your phone?